Hello everyone, welcome to the fourth session of Seminar Information Extraction. My name is Haixun Gu and I'm very glad today to introduce you the two information extraction systems, Textrunner and Noit-R. So first of all, let's have a look of the structure of my presentation. At first, we will have an overview of Noit-R. It is a system developed before open information extraction system, and the second part is our most important part today, which is also the first open information extraction system. And the third part is a short introduction to OCRF, and it is an updated version of Textrunner. So first is our motivation. Why would we to develop Noit-R? So by traditional information extraction, we usually need so many hand-tagged training examples, and the corpus must be homogeneous and small. If we shifting the function to some heterogeneous and big corpus, then it will be problematic. So as Noit-R, we want to develop or design a system which is domain independent, which means it can extract all the information from all aspects of fields, and it is scalable. So it means we can extract more relations, go on and go on. Of course, it is unsupervised, which means all the job will be automatically finished by the system itself. So it is a flowchart of our structure of Noit-R. The three important modules: bootstrapping, extractor, and assessor. As you see in the figure 1, the two inputs are information focus and root templates. Bootstrapping will use these two inputs and creates a set of extraction rules and discriminators. Here we refer discriminators to discriminator phrases. It looks a little like extraction rules. I will explain you a little bit later. And extractor will use the extraction rules to extract the facts we need or we are interested in, and the assessor will apply a probability to each extraction which is extracted by extractor and stored it in our knowledge base. So the inputs first is information focus. It is a set of predicates that represent classes or relations. Actually, classes is also relationships. It is a unique relationship, or we call it a unary relationship. If it is binary or n-ary, we call it relationships. So here are some examples. Have a look at figure 2. The predicates city and country and film and movie actor. These are unary relationship, so we call it the classes. And the capture of city and country and stars in movie actor film. These are two binary relationships. So, and the predicates also give one or more labels for each class, and we do this to improve our records, because sometimes we not only say city but also town. And for country might be a music type, so nation, we plus nation to make it more precise. And another input is root templates. It is designed and created manually by some professor or someone. And figure 4 are a little examples. The first 8 are 8 unary relationships. So non-phrase and other class 1, non-phrase or other class 1, and so on. And the last 2 are two binary examples. So in detail, it's figure 3 is a root templates in detail. So it consists of predicate, pattern, constraints, and bindings. So here, have a look at the constraints. Head of non-phrase 1 is the label of class 1, is a plural of label of class 1. So if we have here class 1 as city, then the head of non-phrase 1 will be cities. And it will check each element in non-phrase list 2 is a prop noun. Here, one heuristic we use are whether the first letter of the noun phrase is capitalized or not. So now it's bootstrapping. Bootstrapping uses the root templates and information focus to create a set of extraction rules. So here figure 5 and figure 6 are two examples. Figure 5 is a unary example and figure 6 is a binary example. As we see, it looks very much like the root template itself, but what's difference is the predicate is no more class 1 but city, a specific class, and we have what's more is the keyword city such as it was created. So here the pattern is non-phrase 1 such as non-phrase list 2. City with the predicate with this pattern, and the output is the keyword city such as. So if we have towns, so we will have towns such as, and the pattern for other patterns, for example, including, then we will have cities including, or cities is the, and etc. And the keywords will be sent to the search engines as queries. It is, yeah, it actually extractor do this also. And not only extraction rules, the bootstrapping created also a set of discriminator phrases. As I just mentioned, we have 8 unary patterns. So from these 8 unary patterns, we will have 8 keywords, and these 8 keywords plus the class name. Then we will so 8 plus city x, then it's 9, and plus x city. Then we'll have totally 10 discriminators. So but these 10 discriminators are not all proper for each classes, so we need to train them, and we want to only select the best k discriminators. Here k by the experiment of the authors of this paper, they choose k equals 5. So now to training. First, bootstrapping sends the queries, which is the keywords, to several search engines and applies the extraction rules to the resulting web pages, and it will get some candidate seeds. And there exists a restriction to the seeds, which is here. Each seed must have a minimum hit counts for the instance itself. So for example, if the seeds, if we have candidate seeds New York, and we Google it, and we have, for example, 10 million results, then it's okay. If we have another city, or fast, or it's something which have only 5,000 results, then we see the hit count is too less. We don't take it as a candidate seeds. So, and these are the choose of the positive seeds, and we do also need some negative seeds. The negative seeds will be chosen with the from the positive seeds of other classes. For example, we want some we want some negative seeds for city, then we choose some positive seeds from country. For example, New Zealand will be a negative seed for the class city. So now everything is ready. We have untrained seeds and untrained discriminators. The next step to calculate the PMI score. PMI score we can calculate use the equation 1 here. The I is the letter I represents an instance, for example, New York, and discriminator is I is a city, and his D plus I then will be the phrase New York is a city. We Google it, we Googled it, and we will have the hit counts, and it will divide by the hit counts of the sentence itself. So we will get the PMI score. Actually, the PMI score is totally small, no matter even for the positive seeds. So we have calculated the PMI score of each seeds and each discriminator. Then we will rank the candidate seeds by average PMI scores, and we select the best M seeds. So half of the seeds will be used to choose the threshold. So we have for each discriminator and instance, we have the multiple PMI scores, and we will have a log. The positive have the PMI score bigger, and the negative have PMI score smaller, and there will be a boundary between these two parts. And here the threshold is this boundary, which will be used afterwards. So, and the another half MCs will be used to go on training the discriminators. So now we have the trained seeds and untrained discriminators. And now, again, calculate the PMI score for each trained seeds and untrained discriminator. Then select the best K discriminators. So, and again, we repeat the process to retrain the selected seeds and the selected discriminators. And finally, we have our last discriminators. Here, figure 8 is an example of the final discriminators. So it has the discriminator phrase and learned threshold and two conditional probability. So next module is extractor, which is the easiest module of NoteOr. It just receive the extraction rules from bootstrapping and retrieve the keywords from it and send the keywords as queries to several search engines, and then get some web pages and apply the extraction rules to these resulting web pages, and extracted a set of extractions, and send the extractions to the assessor. So here are two examples. Example 1, he has visited almost all major European cities such as London, Paris, and Berlin. So first, it will find the cities such as this phrase, and it will see the non-phrase list after this phrase, so which is London, Paris, and Berlin, and then apply the constraints and bindings to this list, and to check whether London, Paris, and Berlin is the proper noun. Here, the first letter is capitalized, so the NoteOr will say these three are cities. And the second example, there will be no results, because the airport maps, city and downtown maps, there is no capitalized letters, so will be ignored. So here is assessor. Assessor's job is to assess the likelihood that the extractor's conjectures are correct or not, how much correct is. So again, assessor have the inputs which are trained discriminators and the extractions from the extractor module. It will combine the extractor module each extraction with each trained discriminator and calculate the PMI score, of course, with the usage of the search engine. And then it will turn the PMI score to several features, and then these features will be seen as input to a Naive Bayes classifier. Here the calculation is the equation 2. So these are the how does Note-OR work. So now is the analysis. First, advantage. Note-OR is domain independent. We have seen the 8 extraction patterns, which have no restrictions. We can apply the patterns to city, to country, to movie star, to film. So this is domain independent, and the training by bootstrapping, we have just seen it doesn't need any manual labor. So no hand-tagged training data will be required, and of course, as an old version of information extraction system, it has also some problems or shortcomings. And the biggest problem is the inefficiency problem. It uses the search engines go on and over and over. So the bootstrapping uses the search engines, the extractor uses the search engines, and assessor uses search engines also. So it will have very substantial resulting web pages and have much work to do. This is really slow. The experimental results will be shown along with TextRunner. So now, TextRunner, our most today's importance. So as we have the problem with Note-OR, so we want to solve these problems. So one problem by the Note-OR is we have given some relations, and then we extracted some information. But for example, I have found that I have some new relation I want to extract. Then I need to process the entire. I need to do the entire process from begin to the end. So this is something wasting. So the design of open information is maybe we can make it. We can make the input. We only need one input. Is a corpus. We don't need the manually designed extraction patterns. So this is our motivation, and one implementation of open information extraction is our TextRunner system. So structure of TextRunner. Here the rectangles represent the 3 modules: self-supervised learner, single-pass extractor, and redundancy-based assessor. And the sole input is a corpus. We randomly select a small corpus sample and use these small corpus sample and the self-supervised learner to train a Naive Bayes classifier. And at the same time, the single-pass extractor extracts some tuples from the corpus and sends the tuples to the Naive Bayes classifier, and the Naive Bayes classifier will label the tuples as trustworthy or not If it isn't, we will ignore it, and we only pay our attention to the trustworthy ones. So the trustworthy ones will be sent to redundancy-based assessor, and this module will calculate probability for this tuple. So self-supervised learner. Actually, parser works only good by some small corpus. But here why we can use parser, because the corpus is a randomly selected sample corpus, so it won't be very large. So it is we will be capable to use parser. Parser have good precision and recall, which are important by training process. So using the parser, which is designed by Klein and Manning, and to each sentence we will and then find all the base noun phrases, and we marked this by E, so entities. So the base noun phrases means here is an example to be solved problem, will be seen only as a problem, and a beautiful lady will be lady, so etc. And we have for each sentence several entities. Then we will traverse the syntactic structure to locate a relation in this tuple. For example, Tokyo is the capital of Japan. Then Tokyo and Japan will be extracted by the parser as two entities, and by the relation extraction, the capital of will be extracted. So now we have several tuples. Some like know it all. We need to know it is positive or it is negative, because we want to train the classifier. So we label the tuple as positive if all the constraints on the syntactic structure shared by the two entities are met, then it will be positive. Actually, we have some heuristic for the negative set, and for here is an example. Path from EI to EJ should cross no sentence-like boundaries. For example, here before blah blah blah, comma blah blah blah, and if one entity is in the first half sentence, so it's the trading, and the species in another half sentence, and this will be the two entities, and the rule and the relation extracted will be here, as you see, is abundant, and we will know the trading is abundant between trading and the species. It's meaningless. So again, we have the positive tuples and negative tuples, and now we need to we train it, and we need to by the computation of classifier naive Bayes classifier, we need to turn the tuples to features. So here some example of features is I have forgotten to write here. Some examples is how long is the relation? How many words does this relation have? How many punctuations does this relation have? And how many stop words does this relation have? And etc. We need these features and find the threshold, and we can use the naive Bayes classifier. So single pass extractor. also it only does the job to extract the information. So it's used the maximum entropy models to tag each word in a sentence, and then it will use a non-phrase checker to find the entities. And meanwhile, the checker also provides a probability with which each word is believed to be part of the entity. For example, the one example is New York, and this checker can give a high probability to say that the word new is believed to be part of New York. So this is an example. And these probabilities will be subsequently used to delete the tables which have low probabilities. So, and extractor has now the entities, and it will need to find the relations. The method is easy. We have the two entities, and we simply have a look at the text between the two entities and extracted it. And of course, we omit some words, some non-essential words. For example, here, definitely developed, we only extract the word developed. We don't need the definitely. And now extractor have done its work, and it will send the candidates table to the classifier, to the naive-Bayes classifier. Redundancy-based assessor. So after the work of self-supervised learner and extractor, we have a set of trustworthy tuples, and now to calculate the probability, we need to find a number or parameter which is similar to the PMI score in know-it-all, but as we just have seen, the method by know-it-all is inefficient. So here is impossible to use the PMI score, but we need something similar. So here we need to merge the tuples, which means the tuples which have the same entities and relations and from distinct sentences, and we will merge these tuples as one, and we count the number. So here we have three sentences. Little Jack is reading a book. Jack has read a lot of comic books, and Jack will read another new book. These three sentences will output the same tuple. Jack, book, and the relation is read, and the number of the sentences will be 3. So these 3 will be used similar to the hit counts in know-it-all system, and then we use the probabilistic model used in know-it-all system to calculate the probability. So know-it-all has information codes, but TextRunner don't. TextRunner has the tuples, so we need the query processing. Each relation found during extraction will be assigned to a single machine. So it means for a relation A, it will be assigned to a machine for example, machine X. So, but then relation A will not be allowed to assign to machine Y or Z or others. But one machine can have multiple relations. For example, the machine X, it can have relation A, B, C, and so on. And then every machine will compute an inverted index. So we here in TextRunner, we use the leucine to compute our inverted index, because the leucine is a free and open source library. And the inverted index, if we have time, I will introduce you in appendix. So analysis. As traditional information extraction system, we have some specific relations, and we have the corpus. And here we refer the corpus to documents. Then the time will be big O of relation times a number of relations times number of documents. But by TextRunner, since we only use the corpus once, so it's the time will be big O of the number of documents, and by the query processing, and it still needs big O of t log t time to sort and count and access. So here are some data. For each fact, the TextRunner needs 0,036 CPU seconds, and by dependency parser is 3 seconds. And so 3 divided 0.036 is 80 times faster. And in each page, in each web page, there are averagely 18 sentences. So there will be 0,65 seconds. And with 9 million web pages, it will be less than 68 CPU hours. And if we do this job parallelly, it will divide 20. It will be less than 4 CPU hours and 5 additional CPU hours to merge and sort the tuples. And experimental results. Here, figure 11 have given the data of TextRunner and Noit-R. Since Noit-R needs some manually created patterns, so we use the patterns in figure 10, and then we find that the average error rate of TextRunner is 33% lower than Noit-R's. Here is 18% minus 12%, divide 18% is 33%. And also, Noit-R, the relation by Noit-R is given, so it's a fixed number, but by TextRunner will find all the finds all the potential relations in our corpus. And here we manually analyze some results of the experiment, correctness of facts and number of distinct facts. Here first, we choose 400 filtered tuples, and we judge whether the relation was well formed. Here means the relation is meaningful. So example here is located in. So we can build a sentence with 2 entities in this phrase easily. But of securing this will be hard for us to doing this job. And after this, we try to see if the arguments were reasonable for the relation. So again, 2 examples. Well-formed Shibuya located in Tokyo, but 23 located in Tokyo. Something is strange. And also we have a log how many abstract and concrete tuples we have, and the correctness of these two groups. Here is a photo. So in our 11.3 million tuples, we have well-formed relation 9.3 million, and in these relations we have 7.8 million, and 1 million are concrete tuples, and 6.8 million are abstract, and 88.1% are correct. So the concrete tables will be very useful by our query answering. So to see how much distinct relations we have extracted, we need to cluster the concrete tables. So here is with the identity two entities, we calculate we grouped these the several relations in one group. So entity A and entity B, and we have several relations from R1 to Rn. And we have found that only 1/3 tables belongs to these clusters. And in each of the cluster, only three chords and is distinct. So we can calculate. Here is almost 92%. So here OCRF is an update of our text runner. Actually, we use the IFBS classifier to train to judge whether the tables is trustworthy or not, and we train this classifier. But with the NBC NB classifier itself is has some problems. It's usually have the results nearly 0 or nearly 1. So much better is the OCRF, which use the CRF. CRF is a conditional random fields. And the table 1 shows the most sentences can be seen like this, which means actually in our language by English, the relations is not so complicated. So it is feasible to automatically extract the relations. So training. Apply a phrase tracker to the documents and get non-phrases, and we need to by the extraction of entities. Of course, if the distance between these two entities is too large, we won't group these two entities in a pair, and then we will assign some marks in the sentence. For example, here the figure 13, begin of a relation and continuation of a relation, and the O will not be believed to be part of a relation. So here a relation might be born in. And extraction. Extraction is also the easiest module. It uses the CRF to extract our extractions. And here, one thing more to do is to use the resolve algorithms to find relation synonyms. So, for example, sometimes develop and invent have the same meaning. So we use these algorithm. Using this algorithm, we can reduce these synonyms. Here another experimental results. We can see ONB is another name for text runner, because text runner uses naive Bayes classifier. Here is the NB. So we can see that OCRF have done the job much better than ONB. So, questions?
Thank you.
Questions? Sorry, I spent too much time.
Any questions?
And if you want here, but we don't have time, so to appendix, you might be interested to have a look at home. Yeah.
No. Last few presentation, this one.
Yeah.
I couldn't read it all because it was too fast.
Okay. Sorry.
Look at it again.
Sorry.
Here
the P is precision, R is recall, F1 is F1 score. Some people call it F measure. And to calculate this, here precision and recall in appendix.
Okay.
Yeah.
Thank you.
Okay, then thank you. Okay.
I have one question. The offline learning phase, do you have information about how long that took relative to I think the total throughput of Know-It-All and TextRunner is relatively fast, but I was curious to know the ratio of the offline part to the online part.
Excuse me?
I just want to know how fast this thing goes when it's learning, when you're training the classifier relative to when it's being applied.
Actually, TextRunner is much faster than the Know-It-All. The experiment by the author of the paper have the results of Know-It-All about they have spent almost 5 days, but by TextRunner only 85 hours.
For the training or for
the entire process.
Okay, thank you again.